Hi everyone, thank you for coming to this talk. My name is Yu Guo from University of California, Irvine. I'm here to present our work in collaboration with University of Zaragoza. Beyond mean theory, systematic computation of backscattering parameters based on microphysical wave optics. Participating media are all around us, such as cloud, fog, ice, or even more on Eurocene, such as nebulae. Also, there are different kinds of translucent materials in our daily life, such as marble, wax, milk, and human skin. These materials allow light to go through their surfaces and scatter in the interior. Light transport in participating media is typically modeled using the radiative transfer theory. In the RTT, participating media are made of a collection of scattering particles. Here, for simplicity, I'm going to show particles in flatland. As light travels through a participating media, it suffers scattering and absorption events before it reaches our eyes. RTT characterizes the optical property of a medium using a few parameters. While light travels, it will go for a random distance before interacting with medium. The extinction coefficient controls the average of such distance, or mean free path. When it interacts with the medium, it has a chance to be scattered or absorbed. The scattering and absorption coefficients control how likely this happens. If the particle is not absorbed, it will be scattered into a random direction. The phase function controls the distribution of this new direction. People use different scattering models to describe the optical properties. The isotropic media assume that each particle has a position completely random and direction independent. However, the anisotropic media have optical properties with stronger directional dependency compared to isotropic media, such as wood or cloth fiber. In media with positive correlation, for example, cloud, the particles tend to form clusters. The areas with low concentrations have higher transmittance. In order to model the backscattering parameters, we generally rely on Lorentz mean theory. Considering of a single particle in the medium, the Lorentz mean theory rigorously computes the scattered field under an incident electromagnetic plane wave. However, the Lorentz mean theory relies on the assumption of the far-field approximation and independent scattering. For any two particles, the distance between them is infinitely large. Considering the light as a wave, this far-field approximation neglects significant near-field interaction between particles. In the rest of the talk, we will establish a new computational framework for modeling light scattering beyond Lorentz mean theory, and demonstrate how our technique can be systematically applied to compute scattering parameters for various participating medium. For a quick preview, we show renderings of thin slab lit with small area light from behind. Result on the left is obtained using a conventional single particle setting, which only considers the far-field scattering. For the result on the right, we use identical particle counts per unit volume, but consider the near-field particle interference. They have very different visual appearances. Next, I will describe how our method works. To remove the far-field assumption and consider the interaction among all the particles, we go back to the first principle of light transport, Maxwell electromagnetism. Given an incident wave and all the particles' information, including location for each particle, we can do a full wave simulation by solving Maxwell equations to get the scattered field. Theoretically speaking, it should work, but in practice, there are billions of particles in the medium. It is impossible to model them and solve the equations. We don't want to handle such an extensive system, but still need microscale wave optics effects, such as diffraction and interference. Here's our solution. We gather scatters in different clusters and handle near-field scattering in each cluster, but still use far-field approximation between clusters. In other words, we consider the cluster as a big scatterer. Later, we can compute backscattering parameters from the cluster. To handle the near-field scattering, we did offline wave simulation on the cluster with user-defined particle distribution and arrangement, including number of particles in the cluster, the distance between particles, particle radius, and index of refraction of the particles. Then we average the scattered field of several random realizations of the clusters. After that, we compute optical properties from the average scattered field of the cluster. Please see our paper for the detailed derivation. After we get the optical properties, it can be readily used in any radiative-based light transport simulator. Here we show example with different realizations of the same medium and their averaged correlated phase function. Next, we first validate our technique by comparing backscattering parameters computed with our method and the Lorentz mean theory. Note that if each cluster only contains one particle, our method reduces to the previous independent scattering method. To verify this, we compared our results with Lorentz mean theory. We focus on the configuration where a cluster contains only one spherical particle, as this is a fundamental assumption of the Lorentz mean theory. We visualize computed single scattering phase functions at the wavelength 600 nanometers with 3 particle radius, 300, 600, and 900 nanometers. From left to right, the particle size increases, and our results match those given by the mean theory exactly. Now we apply our technique to compute backscattering parameters for a wide range of participating media. Let's look at the first experiment. Here we vary particle size and fix all the others. With 100 uniformly distributed particles, we apply our technique to 3 particle size, 400, 500, and 600 nanometers. As shown here, as we increase the particle's radius, the object appears more opaque overall. For the same medium, which the total particles in the medium is kept the same, we increase the number of particles within the cluster, but with fixed particle size. The interference among particles increases the transmittance of this material. Since our technique is derived using microphysical wave optics, it allows generating multispectral parameters based on a single configuration of particle cluster. On the left is a visualization of phase function with peaked 5 wavelengths. The right image is a corresponding multispectral renderings of a thin slab lit by a small area light from behind. As you can see, the smooth changes in scattering parameters across wavelengths have resulted in a characteristic rainbow-like effects. Our method can support any kind of particle distribution. In this example, particles follow an anisotropic Gaussian distribution, as illustrated in the left image. We use tabulated optical parameters since they are all directionally dependent. As a result, different medium orientations will have very different looking. Next, we compare the effect of introducing microscopic correlation in the cluster, but the clusters are uniformly distributed in the medium. Different correlations have a significant effect on the final appearance of the translucent materials. To summarize, we introduce a new technique to compute backscattering parameters for participating medium. Our technique models a translucent material as a cluster of particles distributed in embedding medium. We modeled a wide range of participating medium by modifying the arrangement of particles within each cluster, including isotropic, anisotropic, and spatially correlated medium. While considering the effect of the near field on clusters, our work is still based on the RTT. We cannot accurately model the scattering in the intermediate region, which we treat as far field. A more accurate representation would further enhance the generality of our theory. Our current implementation requires pre-computing the backscattering parameters of the medium by solving Maxwell equations. It is pretty expensive with a large number of particles and large particle size. Finding faster approximations for our scattering function is interesting future research. And to extend our theoretical work to fitting real-world measurements, we need efficient inverse fitting techniques. Please see our paper for more details. Thank you for your attention.